Hi everyone, today we're going to look at the first topic titled Airport Classification under the course Alternative Transportation System CEC 412. This course is designed for HND 2 students in the second semester of the HND 2 program. First thing we'll start with is to define an airport. An airport is an aerodrome with facilities for flight to take off and land. It can also be defined as a complex of runways and buildings for the taking of, landing and maintenance of civil aircraft with facilities for passengers. So, the basic function of an airport is to aid the taking off and landing of aircraft. As civil engineers, our work is to ensure that we design an airport to accommodate taking off and landing without hazards or with minimum hazard. We ensure that the aircraft, while trying to take off and land, it will do so successfully and also provide the necessary facilities such as putting the required pavement, putting the required terminal, apron, hangar, and other components of an airport. An airport is usually equipped with hard surface landing strip, a control tower, a hangar, an aircraft maintenance and fuel or refueling facilities. Airports are divided into Landside and Airside. So we have the Landside and the Airside. The Airside is specifically for the aircraft, for flight takeoff and land, while the Landside is for other things which supports the taking off of the aircraft, the terminal facilities, the lodging in. So here we say Landside include areas such as check-in, parking lots, public transport, railway stations, and access roads. Airside includes all areas accessible to the aircraft, including runways, aprons, ramps. Passage between Landside and Airside is tightly controlled at all airports. The next thing we look at is the International Civil Aviation Organization, ICAO. The International Civil Aviation Organization was formed in 1947 under the auspices of the United Nations and is established Flight Information Regions, FIRS, for controlling air traffic and making airport identification simple and clear. The world's nations claim the right to control their own airspace, that is the portion of the atmosphere above their territorial jurisdiction, up to reaching space limits of between 80 to 100 km from sea level. For navigational purposes, this airspace is typically subdivided into classes, each with their own flying rules. Airspace classification and their flying rule may vary between countries, although most countries follow either the ICAO's classification or a modified version of it. Airspace limits are shown in official charts. We need to look at classification of aircraft size and runway length. Aircraft characteristics related to airport design. So when we look at how the aircraft properties or physical characteristics affects the design of runway or provision of runway. Aircraft characteristics are essential for the planning and design of airports. Aircraft weight is important for determining the thickness of the runway. Yes, the weight affects the pavement thickness, taxiway, and apron pavements, and it affects the takeoff and landing runway length requirements at an airport. The wingspan and the fuselage length influence the size of parking aprons, which in turn influence the configuration of terminal building. Size also dictates the width of runway and taxiways, and the distances between these traffic ways, and it affects the required turning radius on pavement curves. The passenger capacity has an important bearing facility within and adjacent to the terminal building. The runway length influences to a large part the land area required at an airport. So we're looking at airports or aircraft characteristics which relates to airport design. So the dimension of an airport is size, such as the weight of the aircraft. The dimension, we will talk about the fuselage length, the wingspan length, affects the thickness of the pavement. That is, the weight affects the thickness of the pavement. The fuselage length and the wingspan affects the turning radius of the aircraft. It affects the provision of or the size of the parking apron, and also the configuration of the terminal building. So it has a long way. The features of the aircraft has a long way, or goes a long way in affecting the size of the airport and the design. So we also talked about the passenger capacity, because it also affects how the airport will look like. It affects the design of the airport. So, and the runway length also affects the size of the land provided during the design of the airport, or to accommodate the taking off and landing of aircraft. So we look at classification of aircraft size and runway length. The various runway lengths. Here we have the code elements, code number. We have code number 1 to 4. We have runway length, those that are less than 800 meters. We could name them A, and it accommodates aircraft with wingspan less than 15 meters. Then also the outer main gear wheel of the aircraft should be less than 4.5. The second one falls under code number 2, with the runway length from 800 to 1200, greater than 800 or between 800 but less than 1200. So the code falls between code letter B, and the wingspan is between 15, but it must be less than 24 meters. And the outer main gear wheel span should be between 4.5 to 6. It must not be more than 6. Then the third one is between 1200 to 1800. This is 1800, not 1200. So make necessary correction on this. Then the code is C. The code letter is C. And the wingspan length should be between 24 to 36 meters. And the outer main gear wheel span should be between 6 meters to 9 meters. And the last one we have is code number 4, with runway length of 1800 meters and more. Code letter D. The wingspan should be between 36 meters to 52 meters. The outer main gear span should be between 9 meters to 14 meters. So any other one falls between E, which has a wingspan of 52 to 60 meters, and the outer main gear wheel span should be between 9 meters to 14 meters. So we look at a sketch of an aircraft to be able to understand its characteristics. So here we see classification of aircraft size and runway length. We're still talking about that. Here you can see the wingspan. This is the wingspan, the distance between here to here. This is the wheel tread. This is the wheel tread. This is the fuselage length. This is the length between the front tip to the tail tip. So we call it the fuselage length. Then here we have the nose gear. This is the nose gear, and this is the main gear. Then the maximum height. This is the side view and this is the front view of the aircraft. So we can also call this cross-sectional view, while this is the longitudinal view. The next thing we want to look at is the aircraft turning radius on pavement curves. Remember we said that the fuselage length and the wingspan length goes a long way to affect the size of the parking apron and other facilities. So here we're trying to look at the turning radius when an aircraft tries to make a turn. So this is the radius it takes. You can see from here the part of the nose gear. This is the nose gear and this is the main gear. So you can see what we have here, part of the main gear. This is the radius it turns. This is the radius the nose gear takes. You can see it. Then we have the minimum turning radius. You can see the minimum turning radius for the main gears. The other second main gear, you can see where this only turning radius. While the one at the left, this is the we call this is the minimum turning radius, while this one is the maximum turning radius. So the part of the main gear, you can see its part or its radius. So this diagram gives us a clear view of the aircraft turning radius on pavement curves. The next thing we want to look at is the components of aircraft weight. So based on the weight of the aircraft, we will be looking at the various things or the various terms we use in defining aircraft weight. The first one is operating empty weight. Under operating empty weight, we're talking about the basic weight of the aircraft, including crew and all necessary gear required for flight, but not including payload and fuel. The operating empty weight is not a constant for a passenger aircraft but varies within the seats or seating configuration. So the operating empty weight excludes payload and fuel. Any other thing, the crew and the landing, every other components of the aircraft, excluding payload, which is every load that is paid for, including live human beings or passengers boarding the vehicle and goods that they are paid for. So they make up the payload, and with the fuel, when we exclude these from other things that are necessary for the taking off of the aircraft, we call it the operating empty weight. Then the zero fuel weight, we call the zero fuel weight as the operating empty weight plus the payload. So we'll add the payload and exclude the fuel weight, so we call it the zero fuel weight. It means it contains no fuel. Then the third one is the payload. The payload itself, a term which refers to the total revenue producing load. This includes the weight of passenger and their baggage, mail express and cargo. Then we look at the maximum structural payload. The maximum load which the aircraft is certified to carry, whether this load be passengers, cargo, or a combination of both. Theoretically, the maximum structural payload is the difference between the zero fuel weight and the operating empty weight. So when we look at the operating empty weight and the zero fuel weight, we see that the operating empty weight excludes the fuel and the payload. Then the zero fuel load excludes the fuel. So the structural load does not, when we subtract this from this, we'll be able to get the maximum structural load, which means it excludes the weight of the fuel. Then the next thing we look at is the maximum takeoff weight of the aircraft. So the maximum weight authorized at brake release for takeoff, it excludes taxi and run-up fuel, and includes the operating empty weight, trip and reserve fuel, and payload. So we are looking at the structural takeoff weight. So this weight excludes the fuel that is required for taxiing around before takeoff. So when the aircraft is about to take off, it includes its own structural weight, and which is the operating empty weight, minus that is its own structural weight, or what we look at is the operating empty weight plus the trip and reserve fuel, as well as the payload. So it excludes any other fuel that is used for taxiing around or movement before takeoff. Then the maximum ramp weight authorized for ground maneuver, including taxi and run-up fuel. As the aircraft taxis between the apron and the end of the runway, it burns fuel and consequently loses weight. The difference between the maximum structural takeoff weight and the maximum ramp weight is very nominal. So next we look at the maximum structural landing weight. The structural landing weight capability, or the structural capability of the aircraft in landing. The maximum structural landing weight, we said this is the structural capability of the aircraft in landing. The main gear is structurally designed to absorb forces encountered during landing. The maximum takeoff weight varies between 3,600. The maximum takeoff weight varies between 36,000 kg to 350,000 kg. The maximum number of passengers varies between 65 to 500. Runway length for typical airline aircraft vary between 1,800 meters to 3,600 meters. It will be noted that the heavier an aircraft, the longer it is, and the greater is its wingspan. And as the range of an aircraft is increased, the proportion of trip fuel to takeoff weight increases, while the percentage of payload decreases. So we are trying to look at the minimum and maximum weight of aircraft and the runway length for airlines that should be provided for or to accommodate taking off and landing. We said between 1,800 to 3,600. So these are things we need to consider. Next, we look at the characteristics of principal transport aircraft. We look at it based on the table. We have the average distribution of weight components for passenger turbine powered aircraft. That is 0% of takeoff weight. Here we can see we have range, short range. For range, what do we mean? The distance that an aircraft can fly without refueling that aircraft. So operating empty weight, we have payload, we have trip fuel, we have fuel reserve. So for short range aircrafts, we look at the operating empty weight between 66 to then the payload is 24, the trip fuel is 6, the fuel reserve is 4, medium range 59. Then we also look at the payload 1 or 16, then the trip fuel is 21, and the fuel reserve is 4. For long range we have 44, we have the payload is 10, then we have the trip fuel to be 42 and the fuel reserve to be 5. So we're using this to compare the average distribution of weight components for passenger turbine powered aircraft, then considering the percentage of takeoff weight. Next, we look at aircraft wheel configuration. So based on the wheel configuration of an aircraft, we have the single wheel landing gear. For example, we have a DC3. So here we have, you can see this is the nose wheel, while this is the landing wheels or landing gears. So this one has one nose wheel and has two main wheels. Then for the double dual tandem landing gear, example is the B747 to 100. It has two nose wheels and it has about, where we have 4 plus 4, which is 8, plus another 8, 4, 16. So it has 16 landing wheels or gear. So this very one has total wheel of 18, 2 plus 16. This one is 3. Then for the dual tandem landing gear. Example is the B767-200. Here we have 2 nose wheels, and here we have 8 4+4 landing wheels. So we will add this 8 plus 2, which is a total of 10 wheels collectively. Then the last one is the dual wheel landing gear. Example is the DC6. We have 2 nose gears and we have 4 landing gears. So when you add this 2 plus 2, you have 4 plus this. So the aircraft has a total of 6 wheels. So we're trying to look at aircraft wheel configuration. So we'll be able to use it to distribute loads during the airport pavement design. We'll see how these can be useful in carrying out our airport pavement design. Then the next thing we look at is the static weight on the main gears and the nose gears. So based on the diagram we looked at, the distribution of the load between the main and the nose gears depends on the type of aircraft and the location of the center of gravity of the aircraft. So it is dependent on the type of aircraft and the center of gravity of that aircraft. For any gross weight, there is a maximum after and forward center of gravity to which the aircraft can be loaded for flight in order to maintain stability. The stability of the aircraft is very important. The distribution of the weight between the nose and the main gear is not constant. For the design of pavements, it is normally assumed that 5% of the weight is supported on the nose gear, while the remainder is on the main gears. Thus, if there are 2 main gears, each gear will support 47.5% of the total weight. So we're going to take a simple example to be able to clarify this point. We look at a simple illustration on aircraft wheel configuration. So here we have the single wheel gear, double wheel, the single wheel landing gear, the double dual tandem landing gear. We have this very one, let's call this 1. This is our 1. Call this 2. Call this 3. This 3, then we call this 4. We're going to use this for this numbering for the purpose of our calculation. So here we have, for our structural design or design of our aircraft pavement, we consider 95% of the weight of the aircraft goes to the main gears, while 5% is being carried by the nose gears. And what do we mean by this? Let's look at what we're talking about. Based on the diagram we have today, you can see this is the nose gears or the nose wheels, while you can see it here, nose gear, while this is the main gear. So here we are trying to say that 95% of weight of this aircraft is carried by this main gear, while 5% is carried by the nose gear. So what we need to do here is we go back to the dimension. We said the maximum takeoff weight varies between 36,000 to 350,000 kg. So let's use this for the purpose of illustration. Let's use these weights to do our calculation or illustration. So here we have, let's go back, we have for our single wheel landing gear, if the total weight of the aircraft is 36,000 kg, total weight, we say is 36,000 kg. So let's call this 36,000 kg. Then it means for this single wheel landing gear, for its own, we want to know the distribution of load on the nose wheel and on the landing gear. So here we said 95% is carried by the nose wheel, by the main wheel, sorry, beg your pardon. We have the landing gear, we have two landing gears, we share 95% of the weight, shared by two landing gears. Then the 5% is shared by the nose, or is carried by the nose wheel. So what we have to do here is our 95% is 0.95 times 36,000, while the 5% 0.05 is times 36,000. So what do we have here? This to be, if we pick our calculator, we have 95% of 36,000, and we have 0.95 times 36,000. So this will give us total weight carried by the nose, or by the landing gear, is 34,000. We call this 34,200 kg, while the remainder of 36,000 minus 34,200 is the 5%. So this is 0.05 by that, or times 36,000. This gives us 1,800. So we have a total weight of 1,800 kg is carried by the nose wheel. So here the nose wheel carries a total weight of 1,800 kg, while the other one, which is the landing gear, they are two in number. So it's going to be for each landing gear, we'll have 34,200 divided by 2, since they are two in number. So this will give us 34,200. When we split it by 2, we'll have a total of 17,100. So we'll have 17,100 kg. So this is the weight on this. Each of these is 17,100 kg. While this very one, its own weight is 1,800 kg. So based on this, for the dual tandem wheel gear, what we need to do is, the dual tandem has, let's first of all say, okay, for the dual tandem for this, the nose, let's say if this dual tandem carries a total weight of, let's say, 48,000. So if it's carrying 48,000 kg, then it means the nose wheels are equal to 2 and represent 5% of the total weight So for the other gears, that is the landing gears, so say landing gears will be equal to, how many do we have here? We have 4 plus 4, 8, is equal to 4 plus 4 plus another 4 plus another 4. That is this, and this. So out of this we have a total of 16. So it is 16 wheels. So let's keep this, we'll use it for calculation. The third one, this is the dual tandem. So for the nose gears there are 2. For the other landing gears we have 8. 4 plus 4 is equal to 8. So let's say this one carries the total weight, or the total weight of this aircraft is 40,000. Then this very one, let's say this one is 90,000. This one is, let's say this one is 38,000 total weight. And why this one is 2, though we said we have total of 4 because the landing gears are 2 plus 2. That's this very one. I have this and this. So when we add it, we will have total of 4. And the weight is 38. So now let's go back to our board. We'll use our board for calculation. So the first thing we have here is our 36. The second one, which is number 2, is the double dual tandem. This one is for, we perform calculation for a single wheel landing gear, where we said that for the single wheel landing gear, single wheel landing gear, we said the nose wheel, it has only one nose wheel. Nose wheel is 1, it's 1 in number, and it carries a total weight of, my calculation, we got 1,800 kg. The total weight is 36,000. Total weight is equal to 36,000 kg. Then the main landing wheel, we'll call it the main gears. This one we said they are 2 in number, so we're going to share the load. They are sharing 34,200 over 2. We said it's 17,100 kg. So this is our first calculation. For the second one, we have already done the analysis previously. So we said it carries a load of, let's look at what we've done. We go back here, we look at what we've done. Then here you can see what we have here for the, we call this the double dual tandem landing gear. So total weight of 4,800 or 48,000, I beg your pardon. Then we have a total of 2 nose wheels and 16 landing wheels. So 2 nose and 16 landing wheels. So this is the dual tandem. So this is the dual, call it the dual tandem. This is number 2. So for this one, we said the nose is equal to 2 wheels, the nose gear. The main gear is equal to 16 wheels, and we are sharing a total of, the total load is 48. Total load is equal to 48,000 kg. So what we have to do here is the 0.45%, this one which is 5%, which constitutes of 5%, which is 0.05. So 0.05 is 5%, multiplied by 48,000, and because there are 2, we divide by 2. So this will be equal to, what we have here is 0.05. We can drag our calculator from here. Let's pick a calculator. Let's use that to show our calculation. So we have this. So here we have, let's do the calculation. Here we have 0.05 times 48,000. This will give us 2,400. We divide it by 2. So what we have here is, we have 2,400, 2,400, split it by 2, and this will give us 1,200 kg. Okay, for the other gears or the main gears, this will be equal to, gives us, we're going to multiply by 0.95%. So we'll times it by 48,000 and divide this by 16 wheels. we have a total of 16 wheels. So let's see what we have. So go back to our calculator. We said 0.9595 multiplied by 48,000. This will be equal to this. We have 45,600. 45,600. This is the total weight. We divide this by 16. So this will give us a total weight of, go ahead and divide this by 16. Divide by, okay, 45,600. We divide it by 16 wheels. So this will give us a total of each wheel. Each main wheel carries a total load of 2,000. Total load of 2,850. 850 kg. Okay, so we now go to the third one. We drag our calculator down to have enough space. So for the third one, talking about the third aircraft type, we go back and to our former calculation. Here we have, we say this is the dual tandem. This one is double dual tandem, number 2. Number 3 is dual tandem. It has 2 nose and 8 main gears. So we have 40,000. So go back to our calculation. We call this the dual tandem. And then this one is double dual. Call this double. This double dual tandem. This one is dual tandem. So for the dual tandem, the total load is 40,000 kg. Then the nose, we said it has 2 wheels, and the main gears are equal to 8 wheels. So what we have is, for the nose, we know that 95% of the weight, which this one is for the nose, is 5%, which is 0.05, while for this we have 95, which is 0.95 of the weight. So we times this by 40,000, and they are 2 in number. After timesing it by 40,000, so we are going to divide everything by 2 nose wheels to know the weight on each wheel. Then this one times 40,000, we divide this by 8. So here we have 40,000. We bring back our calculator to be able to perform our calculation. So here we have a total of, we have 0.05 and it's 40,000. So we have a total of 2,000. So what we have here is equal to, this should be equal to 2,000, split it by 2 nose wheels. This will be equal to 1,000 kg on each. Then for this very one, we go back to our calculator. We have 0.95. We multiply it by 40,000. This will be equal to 38,000. So we divide this by 8. So what we have here is 38,000. 38,000. We divide it by 8. So this will be equal to 38,000 divided by 8. We have 38,000 divided by 8. So we have a total of 47,500. 47,500 kg, or 4,750. I beg your pardon. It's 4,750 kg. That's what we have on each wheel. So this is for the dual tandem. So we drag our calculator back and also wipe our board for clearer space. So for the last example, which is the fourth one, the fourth example. Go back to our previous calculation. You can see what we have here. For the last one, we have the total. This one is for the dual wing landing here. This one has an aircraft with dual wing landing here. So total weight is 38,000. Nose is 2, and the landing or main landing gears are 4. So go back to our calculation sheet. Here we have got this for a dual wheel. Go back, say this is called the dual wheel. So the dual wheel landing gear. So write down dual wheel. So we have the nose, total is 38,000 kg. So we have the nose, we have two nose wheels. So this will equal to, we'll look at 0.65% are carried by the nose wheels times 38,000. We divide this by 2. This will be equal to, we'll drag our calculator, we'll have the appropriate answer. Then for the main wheels, or main gears, said is equal to 4 in number, and we're expressing by 95% of the load is carried by these wheels. 38,000, we divide this by 4 since they are 4 in number. So what do we have? We drag our calculator out to perform our calculation. So here we have, for this one, we say we're looking at 0.05. We multiply this by 38,000. So this will be equal to, if we multiply it by that, we'll have 1,900. So what we have here is 1,900 divided by 2. And 1,900 divided by 2 is equal to 950 kg. And for this very one, what we have here is, let's see, 0.95. We multiply this by 38,000. So this will leave us with 36,100. So we're going to split this by 4 gears. This should be equal to, we have 36,100. We have 36,100. We divide this by 4. This should be equal to, so we're having a total of 9,025 kg. So that is the total weight that is carried by the main gears. So the total weight by the main gears, for the main gears we have this, for the nose gears we have this. So we've been able to show how the aircraft weight is distributed: 5% on the nose gears, and then 95% on the main gears. For the 4 aircraft, we are able to illustrate between 1 to 4. The next thing we look at is the runway length. The runway is defined as a rectangular area on a land aerodrome prepared for the landing and taking off of aircraft. Runways may be a man-made surface, often asphalt, concrete, which is a rigid pavement. This one is flexible, or a mixture of both, or a natural surface such as grass, dirt, gravel, ice, or salt. Runway dimensions vary from as small as 240 meters long and 8 meters wide in smaller general aviation airports to 5,500 meters long and 80 meters wide at international airports built to accommodate the largest jets to the huge 11,917 meters by 274 meters lake bed runway 1735 at Edwards Air Force Base in California, a landing site for the retired space shuttle. So this is one of the biggest airports we have, carrying a dimension of 11,917 by 274 meters. So for taking care of retired space shuttle. Then for the runway length, we also have a runway of at least 1,829 meters in length is usually adequate for aircraft weights below 90,718 kg. Larger aircraft, including wide bodies, will usually require at least 2,438 meters at sea level and somewhat more at higher altitude airports. International wide body flights, which carry substantial amounts of fuel, are therefore heavier. They also have landing requirements of 3,048 meters or more, and takeoff requirements of 3,962 meters. At sea level, 3,048 meters can be considered an adequate length to land virtually any aircraft. An aircraft taking off at a higher altitude must do so at reduced weight due to decreased density of air at higher altitude, which reduces engine power. An aircraft must also take off at a reduced weight in hotter or heavier or more humid conditions.